Alright, hello everyone. I hope you guys are doing good. So today I'm going to be discussing the solutions to Codeforces round 775. So this is a combined Div-1 plus Div-2 round, which is actually going on right now. There are still 43 minutes to go. But I don't think it is feasible to try and solve the last problem because very less people have been able to solve it even in Division 1. And up till now, nobody has been able to solve this in Division 2. So I don't think I really will be able to. So I thought about making this video. Why not? So yeah, I'm going to be discussing the first 5 problems from Division 2 from A to E. Talking about the round, I think definitely this round was on the easier side. And that is assuming that I don't get any FSTs and I haven't thought about anything wrong here. But yeah, hopefully I don't get any FSTs, and if I don't, then I think this round is definitely on the easier side. Problem B, I think problem B is not very intuitive. I really liked doing problem B, but problem C I found to be much easier than a general div2C. So I think B and C should have been replaced, like B and C should have been exchanged according to me. And also problem E is really good. Yeah, so that's my take on the round. In general, it's slanting towards a easier round, but some of the problems are really nice. For example, B has a very nice observation, and implementation wise problem E is also good. Right, so that's my analysis of the round. So without any further ado, let's start with the solution to problem A. So this is going to be a quick one. So basically you are playing a jumping game where you are at the first index and you have to jump to the nth index. But the thing is that you can jump only one index to the right at a time. But you also have one extra operation that you can do exactly once. That you can do no more than once, right? And that operation is that you go from any index to any other index. So the thing is that you are only allowed to do this extra operation at most once, right? So we can jump to adjacent locations for free, but if we do this operation, then we can jump to any location, from any location I to any location I plus x. And we need to tell what is the minimum possible number of coins that we need to pay to move from the first location to the last location, right? And yeah, so that's the problem. You can move through adjacent cells for free, but you can do an operation and move from any position I to any other position I plus x to the right, giving away x coins, right? Yeah, so that's the thing. So the number of positions that you will jump, you will have to give away those many coins, right? So that is the problem. So the thing is that if you are allowed to do this operation exactly once, then basically you will not do this operation as long as it is possible, right? So you will try to avoid doing this, because if you don't do the operation, then you won't be spending any coins. So the thing is that you will try to avoid it, and you will avoid it as long as you can. And then when you are forced to do this operation, then you will do an operation which jumps the minimum number of positions, because the number of coins is equal to the number of positions that you jump, right? So yeah, that's the thing. So the basic concept here is that you start from a 1, because the first and the last indices are 1, and you keep going to the right without using the operation. Like you keep going to the right for free until and unless you find a 0, right? So if you have a 0 to the right, then you are forced to move to the right with the operation, right? So now you have to do the operation, okay? And then the question arises, at which possible location should you end your jump? And that's again a simple thing to do. So what you will do there is you will start from the right, and as long as you keep finding ones, you will move to the left. But as long as you just you find a 0, as long as you keep finding ones, you will move to the left. But as soon as you find a 0, you basically are again forced to do the operation. So all in all, the major observation here is that you start from the first 0 to the left, right, and end to the right of the last 0, right? So that's the thing. So you will start from the first 0, you will start jumping from the first 0, and you will jump to the right of the last 0, and this will basically minimize the number of coins that you will spend. So yeah, that's the solution to this problem. Let's just have a look at the code. So basically what I'm doing here is I am trying to find out the first and the last indices on which I will jump. So this is the first index and this is the last index, and their answer is going to be the difference between these two indices. Okay, so yeah, that completes it. So now let's move on to the next problem. Okay, problem B. So this is a pretty vague problem statement. It is actually not very easy to understand what's going on here. In order to get better clarity of the statement, I recommend you to actually read the explanation of the samples which they have provided here. Okay. Yeah. So basically in this problem, what they are saying is that there is a game which involves n players, and every player is just passing the ball. There can be any number of balls, and every player is passing the balls, and you have been provided with the number of passes which is done by every player, right? So you have an array A which says that A of I is the number of passes that the ith player has done. And what you need to tell is you need to tell the minimum possible amount of balls that were involved in the game. Okay, so this is pretty vague, I understand, but you will get much more clarity if you try to look at the explanation of the samples which they have provided. So let's look at the second sample here. Here we can see that the number of players is 3, and the first player is doing 1 pass, second is doing 5 passes, and the third player is doing 2 passes. So they have said that it is not possible to do it using one ball, but it is possible to do this using the second ball. So let's see what's going on. So with the first ball, what happens is that the second player passes the ball to the first player, then the first player to the second player, then second to third, third to second, and second to first. So we notice that by using the first ball, the second player is doing 3 passes, the first player is doing 1 pass, and the third player is doing 1 pass. So we are left with 2 passes of the second player and 1 pass of the third player, and that can be done very easily using the second ball. Okay. So I hope with this explanation the problem statement is clear enough. Let's now move to the solution. So in order to arrive at the solution, I think it is better to forget about the presence of multiple balls and try to place the entire passing situation using just one ball. So what happens if there is just one ball? So if I'll assume that I have just one ball, and I'll try to place all the passes in such a way that I can satisfy almost all of the conditions. Like, so I need to find out the optimal arrangement, the most optimal arrangement which I can get using just one ball. Okay. And in problems like this, I think it is almost always beneficial to look at the maximum element. Okay. So let's just have a look at the maximum element. Okay. Like, let's just look at the player who has the maximum value of the number of passes. For example, here there are 2 players which need 3 number of passes. Similarly, in the second test case, there is just one player who needs 5 number of passes. Okay, so obviously a player can't pass a ball to himself, right? So let's denote all the locations of the maximum. Okay, so let's say this is the maximum, this is the maximum, this is the maximum, and this is the maximum. So I'm assuming that the maximum element has 5 number of passes, and let's say that these are the locations of all the maximums. Okay. Now a player cannot pass the ball to himself, right? So between every 2 locations, there has to be at least one element present. Okay. That's the first clue. So now I will write down the main observation. Also, if there are like 5 people if there are like 5 passes for the maximum element, then there are these 4 locations in between them which cannot be empty, right? So if max element is mx, then there are mx minus 1 positions which cannot be empty. Okay, so this is the first job that we need to satisfy. And the second thing is that if somehow we can do this using just one ball, then we can place all the other arrangements successfully using just one ball. What I'm trying to say is that if I can fill all these 4 gaps successfully, then I can satisfy the number of passes for all the other players which are playing easily. Okay, and that is just a construction which I will show you. So if we can fill all the empty places, then we can do it just one ball. We can do it using just one ball. And the construction that I'll do is also very simple. So what happens is that once you have placed everything, once you have placed all the passes for the maximum person, the person who is doing the maximum here, now what you're trying to do is you're trying to fill all these empty spaces. So you keep in the persons, you bring in the persons, and one by one you fill each and every empty space, and you just keep doing it every time, and all the conditions will be satisfied, right? So let's look at this example here, the first sample case in which I have 2, 3, 3, 2. Okay, so the maximum is 3, right? So this is the first position, this is the second position, and this is the third position. Okay, so in all these positions I have 3s. All right. Now what I'll do is I'll fill all these two empty spaces. Obviously, I have 3, 5, 7. I have 7 elements remaining and I have 2 empty spaces to fill. So I can do that. So what I'll do is I'll take this element, which is a 3, and I will start placing it one by one to the right of all my empty spaces. And it turns out that I have filled all the empty spaces. But what about all the other elements? Well, I can just keep doing it. So now I will pick this 2 and I will place this 2 here and this 2 here. Okay, and now I am left with this 2, and I can just continue doing this, and I can place this 2 here and I can place this 2 here. So what we notice is that if we can fill all the empty spaces, then we can just satisfy all the conditions using just one ball. Okay, and that is the optimal thing to do. So what about if we cannot fill the empty spaces? So if we can't fill all the empty spaces, obviously using our first ball, we will try to have as optimal arrangement as possible. Okay, so what happens is that we have all these empty spaces. Okay, so if our maximum element is m, then we have m minus 1 spaces, right? But if we can't fill all the elements, then that means that the sum of all the elements minus the maximum element, which is m, is basically less than m minus 1. That is what I am trying to say. This is the condition for me not filling all the spaces. Okay, but if that's the condition, then how many spaces can I fill? If the sum is m and I am excluding the maximum element, then I can basically fill sum minus m plus 1 spaces, right? Because if there are m elements, then there are m minus 1 spaces. So if there are sum minus m elements, so if there are sum minus m empty spaces, if there are sum minus m elements, then I can basically satisfy the condition for sum minus m plus 1 elements. Okay, yeah, so right. So now if I have sum minus m elements, what I'll do is that we will use sum minus m plus 1 occurrences of the maximum element on the first ball, right? And now we will be left with some occurrences of the first ball, and there is no other choice that we have because we only have the first ball. So we will have to use separate balls to satisfy each and every occurrence of the maximum. Okay, and that is it. So that's the entire solution. So let's just have a look at the code here. So yeah, first of all, we calculate the maximum element and then we calculate the sum of all the elements. So if sum is equal to 0, then that means there is no ball. Then the answer is 0, obviously. So now I will subtract the maximum element from the sum, and then I will check whether or not I can fill all the empty spaces. So if sum is greater than the maximum element minus 1, greater than or equal to, then I can fill all the empty spaces. So I can do it using just one ball. Otherwise, what happens is that from the maximum element, I subtract sum plus 1 because these many empty spaces I can fill. Okay, so these many occurrences of maximum can be satisfied, but the remaining occurrences cannot be satisfied using just one ball. So I will take another ball for each and every occurrence of the maximum. So the answer will be 1, which is the first ball, plus the leftover occurrences of the maximum, which is mx minus sum minus 1. Okay, so yeah, this is my answer. So this is the solution to problem B. I really like this problem. So now we'll be moving to problem C, which I think is generally easier than problem B. Okay, so till now nobody has been able to solve F. Anyways, yeah, so I will go about this problem really quickly. So what this problem is saying is that we have an n cross m grid, and every position, every cell in the grid has been colored. And what we want to tell is we want to tell the sum of Manhattan distance between each pair which has the same color. Okay, so that's the problem. The problem is find the sum of Manhattan distances between the cells which are colored in the same color. Okay, so that's the problem. Now the solution I think is really simple. The Manhattan distance, for people who don't know what Manhattan distance is, between 2 points x1, y1 and x2, y2, the Manhattan distance is just the modulus of x1 minus x2 plus the modulus of y1 minus y2. Okay. Now, the Manhattan distance, we have to take the sum of Manhattan distance between each pair which has the same color. So it makes sense to look at every cell which has the same color. Okay. So what we'll do is, for each color, we will make a map, and we will map each color with all the cells which are colored in that color. Okay. So that's one thing which we'll do. But the main observation here is that since the Manhattan distance is the absolute value of the difference in x plus the absolute value in the difference in y, we will handle x and y separately. So we will handle x and y separately and then sum them. So this is what we are going to do. Okay. Now the thing is that how do we handle x and y? So let's just forget about handling y and have a look at how we handle x, and we will just do the same operations on y and we will sum them. Okay. So now what we'll do is that for each color, make a vector of the x values of all cells which are colored in that color. Okay. So this is what we are going to do. So for each color, we will make a vector of the x values, that is the row values of all the cells which are colored in that color. Now what we can do is, we will sort this vector. Okay. Now basically we have to look at every pair and take the absolute value of their difference. Okay. And we have to look at every pair only once. So let's just fix the first element of the pair to be the ith element, and then we have to look at every I, which is every j which is greater than I. Okay, so we fix I and look at every j greater than I. Now notice that we have sorted the vector. So for every j greater than I, we will have x of j to be greater than x of I, and the difference which we have to take for Manhattan distance is going to be x of j minus x of I. Okay. So for every I, we need to find this value for over all j's which are greater than I. So, and then we need to sum them. So the sum that we want for every I is essentially x of I plus 1 minus x of I plus x of I plus 2 minus x of I up till x of n, assuming that n is the total number of elements, minus x of I. So we can separate these two terms. So basically what we have is x of I plus 1 plus x of I plus 2 up till x of n, right? Minus some constant times x of I, and this constant is essentially n minus I minus 1, I guess. Let me just make sure what the constant is. Yeah. So this constant is n minus I minus 1 times x of I. And it turns out that we can calculate this value pretty quickly if we just do a prefix sum. That is a very standard thing that people do. So we can just maintain prefix sums, and for every I, we can find out the sum in O1 time. And we will do this for every I, and we will do this for x and y separately, and then we will sum our answer. Okay. So that will give us the final answer. Let's just have a look at the code. Okay. So what I'm doing is I'm mapping every color to their x values and to their y values. Okay, so x of color dot pushback I and y of color dot pushback j. Now I'm sorting the vector first of all, and then I'm creating suffix sums. You can also do it using prefix sums. That's totally your choice. And then for each I, I'm calculating the answer, right? And I'm doing the same thing, exact same thing for y, and then summing both of them up. So that gives me my correct answer, right? So yeah, this completes the solution to problem C. Moving on to the next problem. Problem D. So in this problem, let me just check if someone has solved F. Okay, still no solves. Right. So in this problem, we have an array A of n positive integers numbered from 1 to n, and we call an array integral if for any two not necessarily distinct numbers x and y in this array, where x is greater than or equal to y, the number GIF of x upon y is also present in the array. Okay. So if this condition is satisfied for every pair x comma y, then we say that the array is integral. Otherwise the array is not integral. Okay. So also we are guaranteed that every element in the array is less than or equal to this number c, which will be provided to us. So our task is to check whether or not this array is integral or not. If it is integral, we need to output yes. Otherwise we need to output no. Okay. So yeah, that is what we have to do. So let's see. So there is just a very nice little observation which is needed to solve this problem. That is why I am saying that this doesn't deserve to actually be a division 2 problem D, but it is what it is. So let's see. So array is integral if for every pair x comma y where y is greater than or equal to x, y by x, which is the greatest integer function of y by x, is present in the array. Okay, so this is what we have to do, right? Okay, so how to solve this problem? So what I'll do is I will fix my x and basically I will try to iterate on x. Okay, so we will iterate on x, and once we have iterated on x, we will also iterate on x upon y, on y upon x. Okay, so we will basically do a nested loop in which we will iterate on x and we will also iterate on y upon x. Obviously, if we try to do everything naively, then this will obviously TLE, but there is a nice little optimization that we can do that makes it O of n log n, and we will see how to do it, right? So now we will iterate on y upon x. Okay, so let's say that y upon x is 1. So when will y upon x be 1? So y upon x is 1 if and only if y belongs to, if and only if y belongs to this range, which is from x to 2x minus 1, right? And similarly, if y by x is equal to 2, then we can say that y belongs to this range, 2x to 3x minus 1. And similarly, if y by x is equal to k, then y belongs to this range from kx to k plus 1x minus 1, right? So now what happens is that we can iterate on this value y by x, and what we'll do is we need to check if at all there is an element in this range. So if there is an element in this range, then obviously y by x has to be also in this range, right? So we will iterate on y by x. Let's say y by x is equal to k, and now we need to check if at all there is an element in the array which is present in this range from kx to k plus 1 into x minus 1, and if at all there is at least one element present in this range, then k should also be present in the array, right? And we can just do that easily using prefix sums. So what we'll do is we'll create a count array, and then over that count array we will create a prefix sum array. So prefix sum of I will basically denote the count of all the elements whose value is less than or equal to I. So we can check the number of elements in the array in this range simply by doing prefix sum of k plus 1 into x minus prefix sum of kx minus 1. Okay. So yeah, that is what I am doing here. Yeah. So you can just easily check the number of elements in this array. So if this value, if prefix sum of k plus 1 times x minus prefix sum of k into x minus 1, I'm sorry, this should be minus 1. So if prefix sum of k plus 1 times x minus 1 minus prefix sum of kx minus 1, that is the total number of elements present in this range, is greater than 0, then basically count of k should also be greater than 0, right? So if this is the condition, then I'm okay. But if this is not the condition, if count of k is equal to 0 and this value is greater than 0, then I'm not okay. Then basically it is true that there exists a value, there exists a pair y comma x such that y by x is not in the array. Okay. So now we can do this naively. Why? Because this is just a harmonic series, and the sum of harmonic series, as we all know, is O of n log n. So the time complexity here will just be big O of c log c. So c is only 10 to the 6, so it makes sense that a c log c solution would pass. So yeah, that's the entire solution. Let's just have a look at the code. Okay, so First of all, I am calculating these counts and I'm also calculating these prefix sums. Okay. Then I am iterating on my value x. So I goes from 1 to c. If count of I is equal to 0, then I don't do anything. And now I will iterate on j, where j is nothing but k times I. Okay, so j goes from I and I'm incrementing j by I every time. So this is somewhat similar to the code of sieve of eratosthene. So if you are familiar with that, then you know for sure that the time complexity of this is just O of n log n. And now I will look at the range. So the leftmost limit of the range is j and the rightmost limit is j plus I minus 1 to c, the minimum value among these, right? Obviously, because no element is greater than c. So now if the number of elements which are present in this range is greater than 0, but count of j by I is equal to 0, then the array is not integral. Okay. So yeah, that's the only thing in this problem. So finally, if I'm okay, then the answer is going to be yes. Otherwise, the answer is going to be no, right? So yeah, this completes the solution to problem D. So now let's move on to the last problem that we'll be discussing today. Before that, let's just have a look at the standings. Okay, so yeah. Now this is again a somewhat interesting problem. Let's see what this has to say. Right, so this is an involved problem statement, but basically what this is trying to say is that we have two strings s and t, and like this is basically two arrays s and t, and we need to find the total number of distinct arrays that we can form by permuting all the elements in s such that the resulting arrays are lexicographically smaller than t. Okay, so problem E. We need to find the number of distinct permutations of S which are lexicographically smaller than T. So yeah, this is the problem. So let's see how we can solve this. Okay. For people who don't know the definition of lexicographically smaller, it means that the string s should appear before the string t in a dictionary, right? So yeah, so what we'll do is basically we are going to iterate on the point of difference. We are going to iterate on the index where these two strings differ, where s and t differ. Okay, right. So let's say we are at the first index and we say that s and t differ at the first index. So if s and t differ at the first index and s is lexicographically smaller than t, then we will have to place an element whose value is strictly smaller than t of I, right? Which is strictly smaller than t of 1. Okay. So let's say we are at the first index. So for I is equals to 1, we will have to place an element which is strictly smaller than t of 1. Okay, right. So if we just forget about the constraints for now and we try to look at a brute force solution, the brute force way to do it is, first of all, we will calculate the count of every element present in A. Okay, and then we will just go naively for all the elements from 1 to t of 1 minus 1, because these are the allowed elements. So we will go to all the allowed elements and we will try to place an allowed element at the first position, right? So for every element in 1 to, so for every element j in the range of 1 to t of 1 minus 1, we will try to place it in the first position. So once we have placed an element which is smaller than t of 1, then there are no more restrictions on all the other elements that we can place in S, right? Because once we have our point of difference, our string is successfully made lexicographically smaller than t, right? So the remaining elements can be placed in any order, right? Now remaining elements can be placed in any order. Okay. So yeah, this is it. So the remaining elements can now be placed in any order. And so this is still not very trivial. Why? Because there can be multiple occurrences of any elements. So if I place the any random element in the first position, I'll be left with n minus 1 elements. So the number of ways is not simply going to be n minus 1 factorial, right? So let's see. So let's say we have k places and xi occurrences of the ith element. So this is a very standard mathematical formula which is basically taught to people in high school mathematics or in their classes in 11th or 12th in India. So yeah, if we have k places and we have xi occurrences of the ith element and there are like p elements, there are p distinct elements, then the total number of ways to place these elements is this. It is k factorial divided by x1 factorial into x2 factorial up till xp factorial, right? So this is the total number of ways to place the elements if there are in total k spaces and there are x1 occurrences of the first element, x2 of the second element and xp occurrences of the pth element, where x1 plus x2 up till xp is obviously equal to k. So these are the total number of ways to place the elements. Okay, right. So yeah, so now let's say we have maintained all the counts and right now we are at I is equals to 1. So obviously we have all the counts with us. So what we'll do is now for all the allowed elements, basically we will try to place the ith element if at all it is allowed, right? So yeah, we are trying to place an element j such that j is from 1 to t1 minus 1 and count of j is greater than 0. Okay, so the number of ways to do that is going to be so once we place it, we will have n minus 1 places remaining, right? So it's going to be n minus 1 factorial divided by count of 1 factorial into count of 2 factorial, so on up till count of j minus 1 factorial up till count of n factorial, where n can be assumed to be 2 into 10 to the power 5 because no element is greater than that, right? So yeah, notice that we just have decreased this value count of j by 1 and rest all the values have remained same. So these are the total number of values. Okay, so I have to sum up this expression for all j. So we need to sum up this expression for all j from 1 to t of 1 minus 1, right? Okay, so naively it looks a very difficult thing to do. Okay, but there is a very elegant optimization that we can do here. So notice that count of j minus 1 factorial is nothing but count of j factorial divided by count of j, right? So what we'll do is in this expression we will replace count of j minus 1 factorial by count of j factorial upon count of j. So now the new expression that we'll get is basically n minus 1 factorial divided by count of 1 factorial up till so on till count of capital N factorial, and to this entire expression we will simply multiply count of j, right? And now basically now we want to sum this expression up for all j from 1 to ti minus 1, but notice that this entire bracket is common for everything. So the entire sum is basically just this into count of 1 plus count of 2 up till count of ti minus 1, t1 minus 1. Okay, so yeah, now this is an easy thing to do. How? Because we are already maintaining the counts. So to get this sum, we can do something like a Fenwick tree or a segment tree, which will easily give us these range sums, right? So yeah, now we have our range sum data structure with us and we can just query that to find out this sum. Okay, and we can also maintain this number, which is the product of factorial of all the counts, right? This number can be very easily maintained. It will become more clear in the code. And this is basically just something which we can calculate on the go, right? N minus 1 for I is equals to 2, it's going to be n minus 2 and so on. So now we have all the tools that we need, but right now I assumed that I is equal to 1. What happens when we move from I is equal to 1 to I is equal to 2? Okay, so now when we are moving from I is equal to 1 to I is equal to 2, we are making sure that the first element has to be the same. Why? Because we are assuming that the second element is the point of difference, is the first point of difference, right? So the only thing which we have to do is we have to update some stuff, right? So we have to update some stuff. So at the first position, we have to put t of I, right? So what we'll do is we'll do count of t of 1 minus minus, okay? And we will also update these count values in the segment tree, right? So basically we will update in the segment tree this thing. In our segment tree, we will update count of t1, okay? Now another thing that we have to do is we have to update this number, which we are also always maintaining, okay? We have to update this number, which is the product of all the factorials, right? So count of t1 just becomes count of t1 minus 1, right? So what happens is that let's say we have a variable product of factorials pf that we are taking. So instead of in pf previously we had count of 1, but now count of 1 factorial, but now we count of t of 1 factorial, but now we have count of t of 1 minus 1 factorial. And so essentially what we did is we divided it by count of t of 1, right? So yeah, we will do this update. Pf is equals to Pf upon count of t of 1. And we will just keep doing this, and then we have everything with us. So we can just query our segment tree and find out the answer. Okay. So yeah, I really like this problem. Let's just have a look at the code. Okay, so this is just basic segment tree stuff. If you are not yet familiar with segment tree, you can learn about it. Otherwise, you don't really have to bother about this problem. So yeah, we have these two arrays. We calculate the counts, and then we build our segment tree. Okay, now we maintain this variable product of factorials. Okay, and then what we do is that the variable which we are going to add to our answer is this factorial into factorial of n minus I multiplied by the inverse factorial of the variable product fact. This is this expression, the first half. Okay, so this is the first half. And now to calculate the second half, it is just we just need to query our segment tree from 1 to b of I minus 1, and then we'll take the product, and that will be the final thing that we'll add to our answer. So then we add to our answer. Okay, and now we'll find out the number of occurrences of b of I. If the number of occurrences of b of I is 0, then we can't go any further, so we will just break. Otherwise, we will update our segment tree first of all, and then we will update this variable product of fact. We'll divide it by the count, which is in a sense multiplying it by the modular inverse of the count. Okay, and yeah, this gives us our answer. Finally, we will just output the answer. So yeah, this completes everything that I had in mind today. So thank you so much for watching, and I will see you in the next one.